Chain rule page.
Oh,
yeah.
5, give it to me. What is it? Here we go. 5 from the chain rule.
Y equals cosecant third power
Of x.
or just
Almost
x.
fell.
Cosecant to third power x.
Of just x.
I did not like that.
Like that?
Yeah.
Alright. Listen carefully. We'll do a couple chain rule problems. Okay? Even though we're going to do a lot of chain rule in class, but we'll do a couple chain rule problems. My goal is today, the reason I want to start chain rule right away in class today and just check your homework, see if you got it, throw the answer key up there, and not do a lot of homework in classes. I want to do a lot of chain rule problems because to really get a good feel for it. I also want to teach you a couple of new derivative rules. I'm going to teach you the derivative of e to the x today and natural log of x. Okay, and some of the other derivative rules and how you do those. And then tomorrow I'm going to come back and I'm going to give you a document with all of your derivative rules with the chain rule applied to them. What you're going to start to see is really the derivative rules I gave you aren't really correct because you're assuming there's never a composite function. The reality is most of the problems we do are composite functions. All right, this problem right here is really good. I don't think it's that hard. I think we can make this a lot more complicated, and would you mind if I did?
Can you do this one and then make it more complicated?
Okay, I'll do this and then I'll make it a little more complicated. Now, here's the one thing you need to say up front. Cosecant to the third x is really cosecant x to the third power, and then I think it makes it really clear what's the outside function here when we're doing the derivative of a composite function. What is the outside function? Let me go ahead and say this. It is the third power. The two functions here, if you think about it, if you think about this as composite functions, you would say f of x is equal to cosecant x, and you would say g of x is equal to x to the third power, and then how would the composite be written if I identify those as the two functions? What would it be? F of g of x or g of f of x? It'd be g of f of x. And the way the chain rule works is it's the derivative of the what? Outside time evaluated at the, not time.
I mean, it's a function.
So it's the derivative of the outside in terms of the inside. Let me say that again. The derivative of the outside in terms of the inside times the derivative of the inside. Now I did this for my other class. Let me just go ahead and do it for you guys. Let's say I have 4 composites. Let's say I have g of h of f of j of x. Let's say I have that. How would you do the chain rule with this? You do the derivative of g in terms of all the middle. And here's what all the middle is. H of f of j of, I don't know why I did that, of what? X. So 1, 2, 3, 4, close 4. 1, 2, 3, 4 times, keep going, derivative of what? H evaluated at what? F of j of x times. Now look how I do this. As I do this derivative, listen, as I do this derivative, you've got g prime evaluated at the inside. Once I'm done with g, did g come into the problem anymore? Once g's been taken the derivative of, it doesn't come into your problem at all anymore. Now take the derivative of h, now what does it come in? G or h. So now it's f prime of what? J of x. Now it's times what? Huh? Yep, derivative of j of x. Then times, technically, times the derivative of x, which is just what? 1. Eventually, the most inside part you can get to is x. But the derivative of x is what? 1. That's how I'm going to make this a little more complicated in a second.
Is it always?
Nope, because I'm probably going to put a 3x in there. And then you're going to have to go times. It's probably going to be something in there other than x. Okay? So with that said, you guys get it. You get how the chain rule works, in theory. So now let's put it in practice. All right, so it'd be y prime or dy dx. I'll use dy dx. I get sick and tired of using y prime. Okay? I need to get you used to other ones. So power's the outside. So how would you apply a derivative to the third power? Simple power rule. So you're going to go 3 times cosecant to the what? second x.
Yeah.
No.
Yes.
Because that's evaluated at the inside. We didn't change the cosecant x yet. See, a lot of people want to change the cosecant x as you go. They want to multiply by the derivative of cosecant x. You can't do that yet.
Where does the squared come
Simple power rule. Multiply by 3 and do what with the exponent?
from? Oh, it's right.
Subtract 1 from it, right? So is the power done? Okay, then times the derivative of cosecant x. Billy, you got your derivative rules for your 6 straight functions memorized for today, don't you already?
Oh shoot, yeah.
Okay,
Wait,
so
our
what is the
quiz
derivative of cosecant?
Cosecant is negative cosecant cotangent.
He wasn't here last week, people.
Is our quiz today on that?
I would say so.
I'm rude.
Okay, times, wait, there's one more thing. Times the derivative of the most inside part. What's the derivative of the most inside part?
X.
X, which is just what? 1. Now, the only thing really you can do here, ready? Here's how we simplify this, and this might bother some of you. So you got dy dx, okay? You can bring the negative where? So we can make it a negative 3. The 1 doesn't mean anything. But then we can go cosecant squared times cosecant x is really cosecant to the, it's back to cosecant to the 3rd. Because you got cosecant squared times cosecant to the 3rd. Okay? Give me a harder chain rule.
There isn't any others.
What? Yeah, it's a dumb answer. It looks crazy, doesn't it? Can I make one up? 21, what does it say?
What?
F of t.
No, no chain rules.
1 over 2 minus 3.
Yeah, that was good.
Alright, there's 2 options for this.
No, whole thing squared.
Whole thing squared? Well, that doesn't matter because the 1 squared is still 1.
Yeah.
Okay, this is the same thing as 1 over t minus 3 squared because you square the 1, then you can just square the bottom. Okay? Agree? Okay. Here's how you can do this. You can use quotient rule. But I'm going to tell you, now that we got chain rule, get out of the quotient rule every time if you can.
I know.
Okay, if you can get out of the chain rule, get out of it. Alright? So how could I get out of the chain rule, or quotient rule? How could I get out of the quotient rule?
You can move to the top.
Exactly. Okay? So we're going to go t minus 3 to the negative 2. Now the benefit to that is now instead of using quotient rule, which we would have had to do, because the t minus 3 wasn't on top, so I couldn't use constant multiple rule. Okay, you would have had to use quotient rule, derivative top times bottom, times derivative bottom times top over the bottom squared. Now the benefit of chain rule is chain rule will get you out of the quotient rule more than anything else. Because now you can just use chain rule with it. You can look at it and say, okay, the outside function would be the what? What would be the outer layer of the onion here? The negative 2. So you go negative 2 times t minus 3 to the what? Negative 3. That's the power. Now you do times the derivative of the inside. Now be careful because there's sometimes this derivative of the inside might be different. But what is the derivative this time of t minus 3?
Un.
So that's kind of nice. It's 1. So final answer would be this. Negative 2 over t minus 3 to the 3rd. Done. And that's really nice because quotient rule would have taken a lot longer.
You just like plug the second power in each one of those two second power. T squared minus 9.
Nope. Because if you would have gotten 1 over t squared minus 6t plus 9, when you move that top, you're still going to have the whole thing. It's going to end up being 1 times t squared minus 6t plus 9 to the negative 1. I don't know how to raise this to the negative 1, and neither do you. And up here, where it was a negative 2, how do you expand the binomial with a negative exponent? You can write it out, but you got to move it back to the bottom. Eventually, you have to get rid of the negative exponent. You can't do simple. You can't. It's really hard. The only thing you can do whenever you see a negative exponent, you have to move it to the basement eventually, and then it forces you back into quotient rule. So, no, you cannot do it with simple power rule. This one, you had to use chain rule. There's no other way. I'd like it if there were, but when you got negative exponent, it really that makes things messy. Okay? Negative exponents are hard to get out of unless you move them to the basement, and then you're usually forcing yourself into quotient rule, which is really not what we want to force ourselves to do. Okay, I can do one more problem, then we'll stop. Last problem. Is there another chain rule one?
Oh, baby.
Or can I just make one up really, really hard?
Sure.
You want to try it? Alright, here we go. Try a really, really hard one. Okay, you sure you're up for it? Alright. So, here we go. F of x equals 5 times sine of tangent squared 4x. And this is sine of tangent. And I'm going to go ahead and tell you there's a lot going on here. Just write down on paper what you think it is. I'm going to say it's pretty long. Now, I said yesterday, most of the time, the outside function is the power. And that is true for part of this. But you have to look at this very carefully. Where is the square on the outside of the tangent? That's it. Because the tangent squared 4x is inside of what? The sine. It's inside of the sine, so that makes it tricky. And that's not sine times tangent, that's sine of tangent. So this is not product rule. There's no product rule here. And people are like, how am I going to tell the difference between product and quotient rule? I told you how to tell the difference between product and quotient rule. This would be product rule if I would have x there. Then actually the problem's easier. It would just be product rule. But because there's not an x there, now it's chain rule. Alright. Give me time to think about it. Does anybody want to take a shot at it? Now, what is the most outside part of the whole problem? 5 sine. You gotta start with that. The 5 sine is the most outside part of the whole problem. So I'm gonna go the derivative of 5 sine of the inside. Okay, and the inside I can't even touch yet because I gotta start with that outer layer, crusty layer, and get rid of the crust and throw it away. Okay, so what is the derivative of 5 sine? So it's gonna be, watch this, 5 cosine of the inside. Now, here's what I do. When I get a real long, messy one, I check things off when I get done with them, so the 5 sine's done. You don't even, now you look at a whole new problem. Okay, it's a whole new world. Okay, you don't even have to look at the 5 sine anymore. Okay, so now we're to the inside. All right, so now what do? You do the 2 first, the squared. The squared is the outside now. Okay, very good. So it'll be 2 tangent what? Now check off the power. What do you do now? Very good. Some of you got to change them down. It'd be secant squared 4x. Now what do you do? Times 4.
Anything you can do to that, or is that your answer?
Yes, you can simplify this sum. Here's how we can simplify it. We can bring the 4. Look, guys, we got a 2 and a 4. Where can it go? Since all of this is multiplied, where can it go? If it's all multiplied, it can go up front, and that's where you want to bring it, and that's where you're going to see it. So it's going to be what? And there's a 5 too, where? Well, I already know the 5's up front. So 2 times 4 is what? 8 times 5 is 40. So those are done with, okay? What about tangent squared 4x times tangent 4x? Tangent cubed 4x. Times secant squared 4x. Done. Oh my gosh, I couldn't do that. Scratch all that. Alright, 40, I can do the 40. This is cosine of that. I can't put it with that one. So it's 40 cosine, thank you, Mason. Pains me. Times tangent 4x times secant squared 4x. Don't worry, buddy. I'm going to put salt in your wounds, dude. Okay? The reason I can't put this tangent squared 4x and this tangent 4x is because it's cosine of this one. So this thing is just one big mess. Okay? So sorry, I didn't even pay attention to cosine. Alright, we'll see you guys later. Oh! If anybody has like 20 free minutes,